Dear engineers, welcome to VEDA Gate Academy and welcome to the world of opportunities. The topic here is sequential logic circuits, sequential digital circuits, under which the very first topic, flip-flops. And this has a vital role in understanding the complete sequential circuits, one, and also a very important role in competitive examinations with good questions. So this topic has a lot of importance in understanding. And if we raise a question to the student out of digital logic design, which topic you generally feel tougher? And majority of the people says sequential circuits. I don't understand why sequential circuits people feel tougher. And there would be a key for every door to open. If you go in a proper manner from the beginning of a base, I hope you will be very happy to understand the topic sequential circuits. Let us see how would we make this topic learning easier for your future requirements. The very first topic is flip-flops. Now let us learn the definition and the comparison between a latch and a flip-flop. Very beginning. Both are storage elements. Both are 1-bit storage elements. 1-bit storage elements. You can also say cells, elements by cells, to store binary data. Like storing 0, reset condition, storing 0 under reset condition, comma, storing 1 under set condition, comma, no change in output. I repeat, no change in output, called as previous state condition. So 3 states are existed for a latch or a flip-flop: storing 0, storing 1, no change in output. Both are 1-bit storage elements or cells to store binary data. That is how the basic definition of a latch or a flip-flop. Till here, there is no difference between latch and a flip-flop. Then the difference comes here as, right. Without timing control, that is latch. So with the timing control, that is flip-flop. Without timing control, with the timing control. And there is one more definition, latch and flip-flop, in different books given, where level triggered or latches and edge triggered or flip-flops. So different people just say it in different ways. But primarily, without timing control, latch; with timing control, flip-flop. Major differences. So what are the basic latches we have in our syllabus, and one by one to look into the details of that. Basic SR latch and the details of that. And SR latch conversion to others. I'm sorry. SR to D flip-flop, JK flip-flop, T flip-flop. And we have realizations of flip-flops. Realization of flip-flops. That's what you call it as interconversion. And then we have sync and async inputs. Sync and async inputs. And then we have racing and elimination. And then we have master-slave flip-flop. Briefly, these are the topics to learn in flip-flops. Now, let us see. In detail, we'll go one by one to learn about. If you understand the flip-flops in a proper manner, counters, registers, memories would be just playing a game. Because the components behind the counters, registers, memories are all nothing but flip-flops. Let us see in detail. Basic SR latch with 4 NANDs and analyzation. I just want to start the topic flip-flops through a question, and which is most familiar question. Just see the question and then try to analyze that, and then we'll discuss on that and start from the base of flip-flops. I'm here with, hope you remember basic SR latch with 4 NANDs, which you might have already drawn in your academics. Yeah, I remember the standard SR latch diagram is here. 4 NAND gates. Like this. Here they join both. Here also they join both. Like this, like this. The other way you connected this way and that way, giving notations, directions, it would be enough to know. So here, yes, R, Qn plus 1, Qn plus 1 bar. This comes here, Qn plus 1 bar. And this goes down, Qn plus 1. Other way you learned in this way, right? This is connected here, this is connected here, cross coupling. So then giving you a cross coupling, I felt this is a better way. So now, this is what a standard SR latch for 4 NANDs. Just storing the data. Now I have a very important doubt on the circuit. Not only that I raise, but also you need to get that doubt. Whenever you learn this topic, or whenever you see this diagram, with the knowledge of digital logic gates, you must definitely raise a doubt. Firstly, I all wish you to guess what doubt you need to raise. Just see the circuit. What doubt you need to raise the doubt. The doubt is not related to circuit operation. The doubt is related to circuit components and circuit structure. Yeah. Circuit components and circuit structure, you need to just raise an immediate doubt. Yeah. In fact, frankly speaking, I raised this doubt when I was in engineering to my professor. Yeah. From there, I got the analyzation. I already explained you, engineering is not the one to learn what it is, and it is always the one to learn how it is, why it is, where it is, when it is. The student of 20 plus years of matured age need not to be in the class to learn what is what. And always you need to analyze why, where, when, how. And that's how you become a real engineer, to work with the industry. Okay, now what question you're supposed to raise? Can I? Yes, I am. Let me distribute this diagram into two parts. I just wish to take this diagram into two parts. This as one part and this as one part. By your understanding, just see the circuit, and here are two NAND gates. Whenever NAND gate is joined with both the inputs, what it becomes? Is it not an inverter? Yes, it is. So now what will be the output of the first two NAND gates? So yes, joining both NAND gate, no, joining both, it will be inverter. So it will be S bar and it will be R bar. My question is, so, and this is latch, I repeat, I just want to write down the signal, sorry. And this part is for inversion to inputs. And this part is storage part. And your latch part is this only. Now my question is, when your requirement is storage, why do we need inversion to the inputs? I repeat, when your requirement is storage, why do you need to invert the inputs? So the question here is, why inversion to inputs? When our requirement is storing the data. When our requirement is storing the data. Then there will be an immediate question raised. What happens if inverters are there? Yeah, what is your objection if inverters are there? Can I show what is my objection if inverters are there? Here. Inversion here may increase. I'll show you what is that. Anyhow, would you agree that this complete story for storing 1 bit and this is 1 bit for 1 bit to storage. This complete structure for 1 bit storage, 4 gates. Now I want to take an example of here. Say 1 MB memory. 1 MB memory chip. 1 megabyte memory chip. 1 megabyte in the sense 2 power 20 into 8 bits. Byte is 8, right? 2 power 20 into 8 bits. 2 power 20 into 8 bits. You see, for 1 bit storage, 4 NAND gates. So, how many NAND gates are required? NANDs required. So, 2 power 20 into 8 into 4. Isn't it? Because each cell we have 4 gates, no? I already declared. Each cell we have 4 gates. So, 2 power 20 into 8 into 4 gates. So, would be greater than a million. Obviously greater than a million. In this, half of it, that means 2 for inversion, 2 for storage, right? 2 for inversion, 2 for storage, right? So half of it, 1 by 2, 1 by 2. For inversion, half for inversion of inputs, half for storage. In 1 MB chip, greater than a million gates for inversion of inputs, greater than a million gates for storing the data. So, if in 1 MB chip, greater than a million gates are involved in inverting the inputs, what all increased? So, inversion here may increase. Yeah, the parameters. Cost, complexity, comma, size, comma, weight, comma, delay, comma, power consumption, etc. So, inverting the inputs here without a reason is increasing the cost, complexity, size, weight, power consumption, a lot, delay. And what if the inversion removed? Why did the designer given the inversions? There must be a reason, right? So, engineering is analyzing that reason. From there, if you learn, and you are perfect. Now, yeah, why the inversion to inputs? So, inversion is increasing, so many drawbacks. To know why the inversion, I'm here just giving a hint. Can I? To know the benefit of using inverters, can we remove the inverters? Can we remove the inverters and observe the behavior of latch? I repeat, remove the inverters and observe the behavior of the latch. You may be knowing the reasons. Remove this part, use only storage part, and then you may be knowing the reasons. Shall we? That's how the analyzation comes into the picture. Now, I wish to explain basic SR latch with only 2 NANDs next, not 4 NANDs. Hope my question, my theme, and my analyzation is clear with you all. From here, if we learn the introduction of flip-flops, excellent. Yeah, let's go ahead. Basic RS latch with 2 NANDs and drawback. You need to remember one thing. Here, my order is SR. In my next title, I went with the order RS. Yes, purposefully, wantedly. I'll tell you the reason why did the order of inputs are also changed. Previously 4 NANDs, but here only 2 NANDs. Now let me give you the analysis of this. If the structure of RS latch drawn with only 2 NANDs, how it will be? Yeah. Here I'm drawing 5 diagrams to study different cases. Yeah. The input-output conditions are yes, Qn plus 1, Qn plus 1 bar, Qn plus 1, Qn plus 1 bar, or yes, Qn plus 1, Qn plus 1 bar. NAND gate behavior is well known to you, right? Any input 0, the output is 1. All the inputs are 1, the output is 0. Any 0, the output 1. All ones, the output 0. Behavior of NAND. By that, let's see how these circuits will behave. Qn plus 1, Qn plus 1 inversion, 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 Qn plus 1, Qn plus 1 inversion. Now the input-output structures are ready. So basic RS latch with 2 NANDs. So we have drawn totally 5 diagrams to give you the behavior of the complete circuit. Let's see how it will be. Now I just want to draw the circuit here. Yeah. Truth table. R yes, Qn previous state, Qn plus 1 present state, Qn plus 1 inversion. Let me write it down. R yes, R yes, Qn plus 1, Qn plus 1 complement status. So now just comment on the inputs. Yeah. This is previous status. This is present. Please remember, previous, present, and inputs. Now let us study one by one the diagrams. Yeah, we will. Diagram number 1, diagram number 2, diagram number 3, diagram number 4, number 5. Input-output relations. The first one, I'm here with R equal to 0, S equal to 0. NAND behavior, any input 0, output equal to 1. Here 1, we don't bother about this. Any input 0, output equal to 1. So here, not bothered, output equal to 1. So when both the inputs are 0, both the outputs are 1. So R is 0, S is 0, Qn previous state not bothered, both the outputs are 1. And you remember, Qn plus 1 bar are opposite outputs. Opposite output should not be the same, but the condition occurred. Opposite output should not be the same, the condition occurred. 1, 1, Qn plus 1 bar. That's what a forbidden condition we say. FB, or you can also say unused condition. So when both the inputs are 0, both the outputs are 1, unused condition. Next case, R is 0, S 1. If it is 0, we don't bother about this. This will be 1. This 1 will come like this. This 1 will come like this. And 1 into 1, 0. So when R is 0, S is 1, output is 1, the opposite 0. When R is 0, S is 1, previous are not bothered, 1 and 0. So next, third case, when R is 1 and S is 0. If S 0 means we don't bother about this, we'll get 1 here. So the same 1 will turn around. So 1 into 1, we get 0. Right? So when R1, S is 0, output 0. When R is 1, S is 0, output is 0, opposite is 1. The last case, when both are 1. Yeah, here. When both are 1, previous state will come into the picture. Previous state. If it is 0 previously or if it is 1 previously, we should see what is next. If I start with 0, start with 1. If I start with 0, this 0 will be coming here. Any input 0, output equal to 1. And this one will be coming here. And both the ones 0. So if I am starting with 0, this 0 will come here. Any 0 output is 1. This one is going there and output is 0 again. So if I start with 0, I got 0 only. So now if I start with 1, that 1 will come here. R1, S1 anyhow. This 1 will come here. 1 and 1. And then output is 0. This 0 will come here. Any input 0, output is 1. See this? Starting from here. If I start from here and the sequence like this and what I got. So fourth case, 0 remained as 0, 1 remained as 1. So Qn comes into the picture. Yes. So can I say in the last two cases, if it is previous 0, presently it is 0. If previous is 1, presently it is 1. Opposite is anyhow 1, 0. Now, can I just comment on this diagram? Yeah, I will. When both the inputs are 0, forbidden case. When set input equal to 1, output set. I should say set. When reset input equal to 1, output reset. I should say reset. When both are 1, so previous state 0 remained as 0, 1 remained as 1. We call this as previous state. So here also complementary 1. I repeat, both the inputs 0, complementary 1 forbidden. S equal to 1, output equal to 1. R equal to 1, output equal to 0. Both are 1, the previous state it remained. Now, this is the circuit. What I got using 2 nans. You can just make the diagram numbers over here. So diagram number 1 is this. Diagram number 2 is this. Diagram number 3 is this. Diagram number 4 and 5 is this. The outputs. Now this is the structure. What I got using only 2 nans. Can I make this shorter? Yeah, I will. R, S, Qn plus 1. Yeah. 0, 0, forbidden. 0, 1, set. 1, 0, reset. 1 and 1, previous state. Right? Previous state is Qn. This short table. Now just try to understand why do we need to introduce 2 more gates for inversion of inputs. I'm happy with this, right? 0, 0, forbidden case, S1 set output, R1 reset output, 1, 1 previous state condition. I need 3 set, reset, previous state. And all the 3 are obtained for me. I'm happy. Yeah. I mean, my RS latch can be very, very comfortable with the 2 nans. Why do I need to invert the inputs and go with 4 nans? And when this is my behavior, just see this. What is the drawback? Just look into this. Yeah, come back to highlight this and then look into the solution in the next stage. Yeah. solution for this. First, let us write the problem once again. RS latch with two NANDs. Drawback and solution, let us say both. Not only solution. Title RS latch with two NANDs. Drawback and solution. Yeah. Now, let me just redraw the table, what is given previously. R, yes, Qn plus 1. Remember, right? R0, S0, forbidden condition. R0, S1, set. R1, S0, reset. R1, S1, previous state. Nothing but Qn. And this is my table. Keeping this aside, I just want to analyze one thing. Assume we have a memory. Yeah. Here is a memory with million lines. Million lines. So whenever we perform a read operation, excuse me. Whenever we perform a read operation, memory with million lines, read operation taking place. Sorry. Yeah, read operation taking place. Now I have two issues. One, the line which you are reading, which we are reading, comment is in previous state, we take a copy of it. The line which we are reading is in previous state, we take only a copy of it. Second one, other lines, yeah, other lines are however in previous state. We are not disturbing them, no? However in previous state. Now highlight one condition here, that is other lines in previous state. The line which we are reading is also in a previous state. So when we encounter a read operation in the memory, you're reading, just taking a copy of the data. So you're not disturbing anything. So the whole memory remains in a previous state. True? Yeah. Now second, when a write function is encountered, write function to one line, the line to which we are writing, will be of course changed, right? Will be overwritten. Will be updated with the new data. Will be updated with the new data. Other lines? Other lines means how many? Million minus 1. So only one line you are writing, right? That line will be overwritten. Remaining million minus 1 lines, of course, remains in a previous state. Remains in a previous state. Now my conclusion is, here. The conclusion is, I just want to conclude. So while reading, the line you are reading in a previous state, others are also in a previous state. You are only taking a copy of the data. While writing, only one line will be updated. Other lines are, however, in the previous state. Funny. So can I overall conclude reading also the memory in a previous state, writing also the memory in a previous state, except one line, and a million lines out of it, one line writing is negligible, right? So out of million lines, writing into one line, only updating is negligible. So can I overall conclude the whole memory remains in a previous state as long as it is read or write operation is performed? Any operation is performed as long as the computer is on? Yeah, I can. Conclusion? The memory ever remains in previous state as long as the system is on. Now, try to understand the logic here. That previous state, what do we want for a long requirement, forever requirement, is obtained by R equal to S equal to 1. R equal to S equal to 1, can I say high power consumption inputs? HPC. High power consumption. So, to obtain previous state, I am always consuming R equal to S equal to 1. Correct? So, just write that statement. To get the previous state, we are giving R equal to S equal to 1. We are giving R equal to S equal to 1. They are high power consumption inputs. High power consumption inputs. So when memory is consuming, to remain in a previous state, if it is consuming a high power, so as longer the computer is on, it is in a previous state. Don't you think a semiconductor component, the longer it is consuming the power, it gets heat generated? Heat. Temperature. And heat and temperature generated definitely may reduce the lifetime and even data security. True, right? So, which may affect on lifetime and data security of memory. The most important point. So, a very important previous state, longer used, previous state got by high power consumption. One more drawback, unnecessary forbidden. You can just note here, forbidden is unnecessary. Unnecessary forbidden condition applied by low power consumption inputs, LPC. So, low power consumption unnecessary has come. High power consumption, very much unnecessary has come. So this is anyhow unnecessary as we declared. Unused, unnecessary. And that is how the drawback of this circuit. So when we have two NANDs and we got this drawback. And one more which is very fine is S equal to 1 set, R equal to 1 reset. And this is good. Set input equal to 1 set, reset input equal to 1 reset, and this is fine. Good parameter. But the drawback is unnecessary at low power consumption and previous state at high power consumption. So one more issue you can just make up. And unnecessary. FB condition yet R equal to S equal to 0. Low power inputs. Now, solution for this is let's go with the next slide to make up a solution. Excuse me. Let's find a solution for this issue. Solution what I'm giving is invert the inputs. Invert the inputs. If we invert the inputs, the output is, could see here, R will be R bar, S will be S bar, and Qn plus 1. How we get? 0, 0 will be 1, 1, forbidden condition. 0, 1 will be 1, 0, set condition. 1, 0 will be 0, 1, reset condition. 1 and 1 will be 0, 0, previous state. Qn. After inverting the inputs, these are how my outputs are. When I make R as R bar S bar, so 1, 1 forbidden, 1, 0 set, 0, 1 reset, 0, 0 previous state. Now try to observe this inputs. High power consumption, forbidden, good. Low power consumption, previous state, also good. But one drawback is appeared here, you see. So R equal to 1, set, reset input equal to 1 set. I'm sorry, it should not be. Similarly, set input equal to 1 reset. This also should not be. So again, drawback is, after inverting the inputs, the drawback is set output for R equal to 1, comma, reset output for S equal to 1. It has appeared as reverse condition. Now it should be R1 reset, S1 set, but here R1 set, S1 reset. One problem is solved. High power consumption, forbidden, low power consumption, previous state. But new problem arrived. So reset 1 set, set 1 reset. Can we do one thing? Can we interchange and invert the inputs? Interchange and invert. Yeah, solution. interchange and invert. Then how would you do? You'll give it as SR, S bar, R bar, and Qn plus 1. Now what you get here is 0, 0, previous state. Let us write in the sequence. 1, 1 interchanging also the same, right? 1, 1, forbidden. 1, 0 will be 0, 1. Yeah, like that. 1, 0, set. 0, 1, reset. 0, 0 interchanging also the same, right? Previous state. Qn. Now all are positive, right? Try to observe this. High power consumption, forbidden state, very good. And low power consumption, previous state, also very good. Set input equal to 1, set, good. Reset input equal to 1, reset, also good. Now, the structure of latch is SR with 4 nands. I repeat, the structure of latch is SR with 4 nands. First we try with RS with 2 nands. And just be back to, yeah, RS with 2 nands. We tried with this. And when we tried with this, the drawback what we got is, this is the table we got. And the drawback what we got this from here is low power consumption with 0, 0 inputs, so unnecessary output. High power consumption with 1, 1 inputs, so necessary previous state condition. When we use a memory, previous state condition has always existed. As long as the memory is on, when you perform a read operation, however the total memory in a previous state, when you perform a write operation, except that line which you are writing, the remaining is in a previous state. So we can just give you a conclusion that always memory remains in a previous state as long as the computer is on with that. So getting into previous state and holding the previous state having a lot of importance, but that previous state obtained by high power consumption, which generates a temperature, which generates a heat, and that may reflect on the lifetime and storage security of the data. Hence, we thought of inverting the inputs. Yeah, we did. We felt invert the inputs. So when we inverted the inputs, one problem solved. Low power previous, high power forbidden. Yeah, we got that. But new problem arrived. Reset to 1, set to 1, reset. So interchanging may not reflect on 1, 1 and 0, 0. They will remain the same. And interchanging is giving solution for 1, 0 and 0, 1. Now after interchanging, the finest table what we got as, so S1 R1 forbidden, S1 set, R1 reset, 0, 0 previous state. Funny one thing observe here, we never thought of understanding the circuit behavior. But in the meanwhile, in the analysis of why 4 nands and why it is like that, and we also got the latch behavior. Finally, what is the standard SR latch behavior? 1, 1 forbidden, S1 set, R1 reset, 0, 0 previous state. I repeat once again, 0, 0 previous state, 1, 1 forbidden, set input equal to 1 set, reset input equal to 1 reset, the standard fundamental of SR latch with 4 nands. Now why not RS latch with 2 nands? RS latch with 2 nands has a drawback of, I repeat, so high power consumption unnecessary. High power consumption previous state, low power consumption unnecessary. And what happens if you invert and if without interchanging, again a new drawback has come. Finally, the order is SR. The number of gates are 4. The very first diagram which we have drawn is the perfect one. The diagram which we drawn in the introduction has become a standard circuit to follow for latch and flip-flop implementation. Shall we look into this? Yeah, in detailed analysis. Standard SR latch with 4 NANDs, circuit, truth table, excitation, character equation. Circuit which we already drawn, but still we'll draw again. The remaining truth table will show input to output relation. Excitation table will show output to input relation. Character equation is a math equation, mathematical relation for input and output. I repeat, character equation is a mathematical relation between input and output. Now let us see one by one how did they get implemented. Circuit, which we have already drawn once again. Notations, please. Yes, R, Qn plus 1, Qn plus 1 bar, complementary of Qn plus 1, Qn plus 1 bar. Now, what is Qn plus 1? Present output. What is Qn? Previous output. Please always remember that. Qn is previous, Qn plus 1 present. Otherwise, you can also say this. Qn is present one, Qn plus 1 is next one. The same language it is, but this is comfortable. Qn plus 1 present, Qn previous. If Qn is given, Qn plus 1 is appearing. Now, the table of this in detail, what we got? Yeah. The short table already we got, right? Oh, SR, I'm sorry. Yes, R Qn plus 1. What is that? 0, 0. Previous state. 0, 1. Reset. Reset means 0. 1, 0. Set. Set means 1. 1 and 1. Forbidden. Forbidden is don't care. What is that? Qn plus 1 is equal to Qn plus 1 bar is equal to 1. That is forbidden. Unused condition. To draw a character equation and excitation, we are supposed to draw the completeness of truth table. Now, let's draw a complete table here. The order is yes, R, Qn, Qn plus 1, Qn plus 1 complement. Yeah. 0, 0. Inputs are 0, 0. So, with previous state 0, 0, 0 with previous state 1. You know well, right? 0 remained as 0, 1 remained as 1. 0, 0 is the previous state condition. Opposite is 1, 0. So, here is highlight the next one. 0, 1. Yes, 0. R is 1. When R is 1, reset. We don't bother about our Qn, previous state. Whether previous is 0 or 1, my output is reset. Right? Because S is 0, R is 1. Opposite is 0. Third case. S is 1, R is 0. When set input equal to 1, here. It is set. R equal to 1, reset. So, previous whether it is 0 or 1, my output is 1 only. So, opposite is 0. The last condition, what we got? Both 1. When both are 1, complementary outputs are 1. Whether this is 0 or 1, we don't bother. These both are 1. Qn plus 1, Qn plus 1 bar, both are 1. Now, let us see the operations. So, highlightings, when both are 0, 0, 0 remained as 0, 1 remained as 1, previous state. When r equal to 1, I'm sorry, r equal to 1, reset, opposite is set, yeah. R equal to 1, reset. Reset is this, opposite is set. Yeah, highlight. When r equal to 1, reset. When s equal to 1, set. When both the inputs are 1, s equal to r equal to 1, both the outputs are 1. Forbidden condition. And this is detailed table. And I want to make a character equation for qn plus 1, mathematical equation with the inputs s, r, qn. Try to understand the character equation. Yeah. F of S R Qn is equal to Qn plus 1. Character equation nothing but Qn plus 1 is equal to, where and all it is high, Qn plus 1 is high in this case, in this case, in this case. You cannot take this because it is forbidden condition. Forbidden is anyhow don't care. So inputs are, as you know, 0 at the input, first input, second input, third input, fourth input, fifth, sixth, seventh. 0 to 7 the inputs. Now try to make up sigma small m, where and all it is 1, 1th cell 1, 4th cell 1, 5th cell 1, 1th cell 1, 4th cell 1, 5th cell 1. So I can say 1, 4, 5 plus don't care 6, 7. The last two tells anyhow forbidden, don't care. Now let me make a K-map and simplify this. Yeah, let us. Here is a K-map. Yes, RQN. Yes, RQN. One, 4, 5, 0, 1. 4, 5, 6, 7, don't care. Don't care. 1, 4, 5, 6, 7. So here are the notations. R bar, QN bar. R bar, QN. RQN. RQN bar. Yes bar. Yes. Now make up the frame. Here is a quad. Here is a pair. So character equation Qn plus 1 is equal to S plus R inversion into Qn. I repeat, character equation Qn plus 1 equal to S plus R inversion into Qn. Now the one left here is excitation table. Let us see the detailed analysis of that. Yeah. Standard SR latch with 4 nans excitation table. Excitation table is output to input table. Outputs are given, inputs to be found. I repeat, outputs are given, input to be found. From the output equation, we can do that. So I'm here with SR output equation. S plus R inversion into Qn is equal to Qn plus 1. I repeat, S plus R inversion into Qn equal to Qn plus 1 are the equation which we have designed in the previous one. Sorry. Here, S plus R bar into Qn equal to Qn plus 1. From this, let us derive the excitation table. Yeah. So I just want to analyze the cases one by one. Qn plus 1, 0, 0. I can get in two conditions. One is 0 remained as 0 previous state. There I may get 0, 0 option. And also Qn plus 1 is 0. There also I can get. So I don't bother about Qn. Qn plus 1 is 0. What is this? This is reset, right? Qn plus 1 0 is reset. Yeah, 0 remained as 0 is previous state. Qn plus 1 0 is reset condition. What must be the inputs? As you know well, define SR. Previous state SR must be 0 0. To get reset S0 and R1. So here S is 0. R0 means R bar is 1. R1 means R bar is 0. Right? Next case. Second case is Qn plus 1 could be 0 1. Yeah, 0 1. Qn becoming Qn plus 1 opposite. We don't have that condition in SR. 0 becoming 1. 0 becoming 1 is toggle. The toggle condition we do not have in SR latch. So only thing we can say set output 1. Yeah. Output 1. Output 1 is set. To get set, what must be the inputs? S1 and R0. S is 1. R bar how much if R is 0? 1. Now come back to the next condition. Third state of Qn plus 1. 1 0. 1 0. Same story. 1 is becoming 0. Qn1 becoming to Qn plus 1 0. Toggle. We don't have that condition in SR. The only thing is set. Sorry, set is over reset. Here 0. 0 means reset. To get reset, what are the inputs? S0 R1. S0 R1 in the sense R bar is 0. The last case. Yeah, 1 1. Qn plus 1 both are 1 1. Yeah, here also we have two conditions. One remained as 1 1 state, and we don't bother about this one, set to 1 state. So here the issues are 1 remained as 1 previous state, 1 condition. Getting 1 set as 1 condition. For us always this is important, Qn plus 1. Sorry. Now come back to speak. To get previous state, what are the inputs? 0 0. To get set, what are the inputs? S1 or 0. Declare the inputs here. 0. R0 means R bar 1. 1. R0 means R bar 1. Over, right? Now, just short out this table. Just make up a simple axis. Qn plus 1, for which we have to declare SR. Yeah. The combinations could be 0 0, 0 1, 1 0, 1 and 1. Try to understand. For 0 0, S is constantly 0. For Qn plus 1 0 0. First case. S is constantly 0. R could be 0 or 1. 0 or 1 is a don't care, right? 0 or 1. So this is 0. This is don't care. For Qn plus 1 0 1 1 0. For Qn plus 1 1 0 0 1. Both 1 and here. S could be 0 or 1. Don't care. R is constantly 0. So don't care 0. Excellent. A well-noted table from here you need to use in many cases. Yeah, this is important even. So 0 0 0 x 0 1 1 0 1 0 0 1 1 1 x 0. So how that has appeared? From the character equation is appeared. From the output equations. What is excitation table? Outputs are known, inputs to be found. I repeat, outputs are known, inputs to be found is called as excitation table. So SR excitation table is given by using SR output equation. Qn plus 1 is equal to S plus R inversion into Qn. The immediate to this, sorry. SR flip-flop converted to delay flip-flop. Now, what are the flip-flops we have in syllabus of sequential circuit? SR flip-flop, delay flip-flop, JK flip-flop, and toggle flip-flop, T flip-flop. D flip-flop, JK flip-flop, T flip-flop, SR flip-flop. If anyone highlights D flip-flop as a separate bond flip-flop, it's wrong. I repeat, if anyone highlights D flip-flop as a separate bond new flip-flop, it's wrong. D flip-flop is nothing new. It is just an updatement, a new version of SR into the other application. Similarly, JK also, T also, all these are the updated versions of SR into some new requirements. Some small modifications have been taken care. If you learn in this way, and you are very simple to do. So, shall we go ahead? Yeah, let us. So, delay flip-flop is SR flip-flop updated as here I just want to give you a short hint. I'm sorry. Before going to SR flip-flop as a D flip-flop, I just wish to go latch converting as a flip-flop. Yeah, that is short note. Previously, we've seen only SR latch. Now, let us see SR flip-flop. Here, adding clock. Adding clock. Come back to speak. Here is what my NAND gates diagram. Yeah, notations. Yes, R. Qn plus 1, Qn plus 1 bar. Qn plus 1, Qn plus 1 bar. Here I'm adding input clock. Yeah, I'm sorry. And this is how my SR flip-flop. Can I say clocked SR latch? Yeah, I can. I can just give the name as clocked SR latch is nothing but SR flip-flop. Now just see the table. Yeah. Clock SR Qn plus 1. Yeah. Let's see if my clock is 0. Yeah, here if my clock is 0, I don't bother about SNR. Correct? Any input 0 resulting internally 1, 1. Did you remember 2-gate circuit? If 1, 1 is given, it went to previous state. That's a drawback we explained. Yes, 2-gate circuit with 1, 1 inputs given. Try to refer. So with 1, 1 inputs given, it went to previous state. So external SR not bothered. Output remains in previous state. The next case, let's work out with clock 1. Clock is 1. Here my clock is 1. If clock is 1, 1 into S, S bar, 1 into R, R bar. It is again working like a same flip-flop. these two are acting like inverters. So circuit is same. If my clock is 1, again they are acting like inverters. S bar, R bar. Story is same. So 0, 0, previous state. 0, 1, reset. 1, 0, set. 1 and 1, forbidden. So I just want to make a comment here that first case circuit is off, right? Output remains in previous states. 4 cases circuit is on, responding for inputs. When clock is 1, it is on, responding for inputs. I repeat, I would say responding for inputs. When clock is 0, it is off. Output remains in previous state. Can I overall say clock is acting like a control input? Yes. That means clock here is a control input to enable and disable inputs. I repeat, clock here is acting like control input to enable and disable the inputs. Now let's see the structure of SR flip-flop updated as delay flip-flop. Yes. SR flip-flop updated as a single input switch. I repeat the feature, single input switch. Single input switch. SR flip-flop updated as a single input switch with the feature important one here, Qn plus 1 of S comma R, or I can say Qn plus 1 is equal to S when S is not equal to R. Try to observe that feature in this table. Qn plus 1 is 0 and S is 0. Qn plus 1 is 1, S is 1. Did you notice? Yeah. 0 means 0, 1 means 1. Qn plus 1 is resembling S when S is not equal to R, 0, 1, 1, 0. When S is not equal to R, Qn plus 1 is S only here. That is the base we took to develop a D flip-flop. So Qn plus 1 is equal to S when S is not equal to R. I just want to make this SR flip-flop 2 input as a single input switch. Single input switch passing one of the input as it is. Which input can I? According to this feature, I can pass S to the output. S is 0, output is 0, S is 1, the output is 1. When S is not equal to R. That means if I create S is not equal to R condition, S will be passing to the output. I repeat, if I create S is not equal to R condition, S will be passing to the output. Here, let me write. That means by creating S is not equal to R condition, S get to the output. Now, as can I say S is equal to D, R is equal to D bar. That's what S is not equal to R condition. Qn plus 1 is equal to D. In bracket, of course, yes. So, draw the diagram. Over. D bar, clock, Qn plus 1, Qn plus 1 complement, yes. So S place D given, R place D bar given, S place D given, R place D bar given. When S equal to D, R equal to D bar, Qn plus 1 is equal to S, nothing but D over S passing. So here, truth table, clock, D, Qn plus 1. If clock is 0, we don't bother about D. It remains as Qn. 0 remained as 0, 1 remained as 1, previous state. If clock is 0, previous state, a blind significance. If clock is 1, D could be 0, D could be 1. If D is 1, if D is 0, S is 0, R is 1. So reset. The output will be 0. We don't bother about this. So we can say whether this is 0 or 1, we get 0 only at output. If D is 1, whether this is 0 or 1, we get 1 only. So it will be D as it is passing. So D0 output 0, D1 output 1. So character equation, can I directly say Qn plus 1 is equal to D? Output equal to input, right? Now, next excitation, ET. Qn plus 1 for which defining D? They could be 0, 0, 0, 1, 1, 0, 1 and 1. Yeah, irrespective of Qn. Here, this is 0 only when this is 0. This is 1 only when this is 1. This is 0 only when this is 0. This is 1 only when this is 1. So Qn plus 1 is equal to D. If it is 0, it must be 0. If it is 1, it must be 1. If it is 0, it must be 0. If it is 1, it must be 1. Qn irrespective. So Qn plus 1 is equal to D, the equation. Excitation table is over. Now I have a very important question from delay flip-flop. Just try to notice. Yeah. And this is how, once again, rehashing delay flip-flop. Delay flip-flop, nothing but SR flip-flop, updated as a single input switch with the feature Qn plus 1 is equal to when S is not equal to R. That means by creating S is not equal to R condition, S will get to the output as S equal to D, R equal to D bar, nothing but S is not equal to R condition. Qn plus 1 will be S, nothing but D given. The circuit table and character equation, excitation table, all are given. Now the question is, delay is a common event in any flip-flop, right? Yeah, delay is a common event in any flip-flop. Delay is there in SR, delay is there in JK, delay is there in T, delay is there in every circuit. Common event. When delay is a common event in all the flip-flops, why this is only the one highlighted as a delay flip-flop? I repeat once again. When delay is a common event in every flip-flop, why this is only the one highlighted as a delay flip-flop? Yeah, guess. Good question, right? Delay is everywhere there. But why this is only the one highlighted as delay flip-flop? Simple. Let me write that. The circuit is SR flip-flop as JK flip-flop. Let it be. And I just want to write down a site. Question is, why D flip-flop is only the one? been called as delay flip-flop when delay is there in every flip-flop. I repeat, why D flip-flop is only the one being called as delay flip-flop when delay is there in every flip-flop? Yeah. Answer. Here, delay is only the action between input and output, unlike others. I repeat, what is SR flip-flop action? S plus R inversion into Q1. Set, reset, previous state, many. JK flip-flop, toggle, the main action. Sorry, J0, K0, previous state, J0, K1, reset, J1, K0, set, J1, K1, toggle. All the other features are there. And T flip-flop, previous state and toggle. But whereas in D flip-flop, no other action except a delay between the input and output. So delay is the main action. So the name of the flip-flop is given based on the action behind it. I repeat, name of the flip-flop is given based on the action behind it. So SR flip-flop is set to reset, D flip-flop the delay main action, JK flip-flop given by John Kilby, the scientist name given, and T flip-flop is a toggled flip-flop. Hence, the answer is here delay is only the action between input and output, unlike others. That is why it is called as delay flip-flop. Now, let's see the very important one. SR flip-flop converted as a JK flip-flop. Let's go ahead. SR flip-flop updated to produce toggle state in place of FB state. I repeat, SR flip-flop updated to produce a toggle state in the place of forbidden state. That is why SR flip-flop has got, the state of JK flip-flop. Remaining all the same, no change. SR flip-flop updated to produce toggle state in the place of forbidden state. Now come back to speak the procedure to get. I just want to ask you one thing. Whether, in any circuit, any subject of engineering or anything, whether diagram comes first or the concept comes first. Of course, diagram. I'm sorry, concept. Diagram is later. But in many cases I have experienced people drawing the diagram first, but not the concepts explained. I just feel funny in that way. You're by-hearting the diagram, working conditions and features. But you're not drawing the diagram. You need to draw the diagram. Now, in this case, let us see to draw the diagram first with the concept. Right? Let us just see the concept and then draw the diagram. The procedure of converting one flip-flop to the other. SR flip-flop to be converted as JK flip-flop. What we want as JK from SR, correct? J, K, Qn plus 1. From where we want? From SR we want. JK, Qn plus 1 from SR we want. Can I do this? Yeah. If I take like this, or I can also take like this. Two different approaches. Yeah. This way, can I say it is JK requirement. And this way, can I say it is SR excitation? You see this, JK, QN, QN plus 1, input, output, JK requirement. And this way, QN, QN plus 1, SR excitation. So, how SR is excited to get converted as JK? That is the requirement. How SR excited to get converted as JK? Are you clear? Now, let us draw the JK requirement first. J0, K0, previous state, 0 remained as 0, 1 remained as 1. Please tell me, how am I doing this? I have already given on the upper stage, SR flip-flop updated to produce toggle state in the place of forbidden state. That means all the remaining states are unchanged. Only forbidden removed toggling is placed. Previous state is same, reset state is same, set state is same. No change in it. So, first three conditions are never changed between them. Come back to speak. J0, K0, previous state, just like S0, R0, previous state. J0, K1, reset, just like S0, R1, reset. 0, R1, reset. J1, K0, set. Whether it is 0 or 1, set. Till here, no change between SR and JK. From here, the change occurred. The last case is 1, 1. 1, 1, it was forbidden, but we want to get toggle state. Toggle state is 0 becoming 1 and 1 becoming 0. 0 becoming 1 and 1 becoming 0. That's what my requirement. Now, let me frame SR based on the excitation conditions here. So, as we know well, for 0, 0, you remember SR excitation? 0, 0, 0x, 0, 1, 1, 0, 1, 0, 0, 1, 1 and 1, x 0. I don't want to draw again. I repeat, 0, 0, 0x, 0, 1, 1, 0, 1, 0, 0, 1, 1 and 1, x 0. In the previous case, I have already explained. So, 0, 0, 0x, 0, 1, sorry, 1, 1, x 0, 0, 0, 0x, 1, 0, 0, 1, 0, 1, 1, 0, 1 and 1, x 0, 0, 1, 1, 0, 1, 0, 0, 1. Now, XR are already found. Now, the simple story is, put them in K-map, draw the circuit. Yeah. Let me draw S equal to R equal to. K-maps here. Yes, RQN. R bar QN bar. R bar QN, RQN. RQN bar. Yes bar, yes. Enter the values. Similarly, draw for the other one also. Sorry. Yeah, yes, sir, are the inputs, correct. Enter the numbers for S and R. Where is yes high? Here. Here. Don't case yet. These two places. So 1 don't care. 5 don't care. 0, 1 don't care. 4, 5 don't care. 4th one and 6th one. 4th one, 5, 6th one. I'm sorry here. Yeah, come back to speak S plus. Yes, Q and bar, that's all. Okay. Come back to speak. Here. So can I say hey, I'm just finding SR. My inputs are J, K, Q, N, right? I'm sorry. J, K, Q, N are the inputs. Sorry. J, K, Q on the inputs. Output is SR. Finding SR. J, K, Q, N. K bar, Q, N bar. K bar, Q, N. K, Q, N, K, Q, N bar. J bar, J. S is equal to, and this is how the structure. A pair here, J into Q, N bar. Right? R is equal to, find out where R is, right? R is 1 here, R is also 1 here. Don't care at these two places. 0th don't care, 2 don't care. 0th don't care, 1, 2 don't care. And 3rd is 1, 7th is 1. 0, 1, 3. 0, 1, 2, 3, 4, 5, 6, 7. So here is this. It is KQN. So finally, S is equal to JQN bar, R is equal to KQN makes SR flip-flop to become a JK flip-flop. I repeat, finding SR in the terms of JK. What modification SR to be taken to get converted into JK is this? I repeat, so whichever the flip-flop you want, the truth table of that, from which you want excitation of that. So when is SR excited to become JK? That's a nature. When is SR become excited to, get JK? Yeah. Come back to speak to draw the diagram. Yeah. SR flip-flop as JK flip-flop. Here is this. S is equal to JQN bar. R is equal to KQN. You remember, right? So yes, please. Notations. And this is what S, this is what R, as we know. Clock. QN plus 1, QN plus 1 bar. So what circuits to be given? In the place of S, I have to give in the place of R, I have to give. What I have to supply? In the place of S, JQN bar, KQN. Now come back to speak. Here, I have to give QN bar, QN. But tell me one thing, I don't have QN bar in the diagram. And I only have QN plus 1 bar, QN plus 1 in the diagram. Try to understand this logic. And this is my SR circuit, which I've already drawn. previously. This is our SR. So modifying it as JK. In the place of S, supplying JQN bar. In the place of R, supplying KQN. But we do not have QN bar in the circuit. We only have QN plus 1 bar, QN plus 1 in the circuit. How shall we substitute? Can you please? Actually, QN bar is not the existed states. They are nothing but QN plus 1 bar and QN plus 1. But the only thing is previous state is connected to that. So whenever we speak about the input level, when these are connected here, always the previous bits will be appeared here. So connection will be given as same QN plus 1 bar, but the one appeared will be QN bar. Similarly, connection will be given as QN plus 1, the one but appeared will be QN. Are you clear once again? So here what do we connect as QN plus 1 only? So here what do we connect as QN plus 1 bar only? But what is appeared at the input level is always QN. And what is appeared at the input level is always QN bar. So when do we get QN plus 1? After the completion of the circuit. But at the beginning level, what will be there? When this is connected, previous bit will be appeared. Previous bit will be QN to this. Previous bit will be QN bar to that. Don't get confused. Equation is JQN bar. But the connection will be QN plus 1 bar only. QN bar has never existed in the circuit. It is the previous state of QN plus 1 bar. Similarly, QN never existed. It is the previous state of QN plus 1. So connection would be the same, but the bit appeared will be the previous bit. Yes or no? It is. So this is previous bit. Here also this is previous bit. So now replace this. This is AND. This is inverter. This is AND. This is inverter. Can I make it as NAND? Why not? So inverter only, no? Sorry. Here are inverters, right? So can I just make this circuit like this? Yeah. So the modified circuit is J QN plus 1 bar K QN plus 1. Intermediate is clock. And here are you clear, right? And inverter, NAND, that's what I replaced. And inverter, NAND, that's what I replaced. Like how the JK flip-flop is structured. And truth table, which we've already seen. Character equation, excitation table. Shall we? One by one? Yeah, let us. Now let us see SR flip-flop to JK flip-flop, character equation and excitation table. One by one. JK flip-flop, truth table with short rehash and then followed by character equation and excitation. Yeah. J, K, QN, QN plus 1, QN plus 1 bar. As we know the table well, J0, K0 previous state, 0 remained as 0, 1 remained as 1, opposite is 1, 0. J0, K1 reset, whether this is 0 or 1 reset, reset means 0. J1, K0 set, set 0, R1, the output 1, set opposite 0, J1, K1, toggle. Toggle means 0 becoming 1 and 1 becoming 0. The highlighting part is here, previous state, here, reset, here, set. So J0, K0, previous state 0 remained as 0, 1 remained as 1. K constantly 1, reset. J constantly 1, set. J1, K1, 0 becoming 1, 1 becoming 0, toggle. And first 6 conditions are exactly like SR, right? Till here. Same like SR. Till here it is exactly same like SR. No change. Let us see the character equation. So here it is 1, here it is 1, here it is 1, here it is 1. So inputs are J, K, Q, N, right? Yes. Map here. J, K, Q, N. K bar, Q, N bar. K bar, Q, N. K, Q, N, K, Q, N bar. J bar, J. Enter the values. 1, 4, 5, 6. 1, 4, 5, 6. Can I structure like this? So character equation here. Qn plus 1 is equal to Jqn bar plus K bar Qn. Jqn bar plus K bar Qn. Now let us convert this into excitation table. Yeah, let us. Jqn bar plus K bar Qn is equal to Qn plus 1. That is how the excitation table, right? Yeah, character equation from which excitation table. Now try to frame the equations. They could be 0, 0. They could be 0, 1. They could be 1, 0. They could be 1 and 1. Yeah. Qn, Qn plus 1, 0, 0, 0, 1, 1, 0, 1, 1. So now from which we have to find Jk. Yes. Now can you tell me two conditions in both inputs? Solve. Yeah. 0 remained as 0, previous state, getting 0, reset. 0 getting 1, toggle, getting 1, set. 1 getting 0, toggle, and getting 0, reset. So, where is it? 1, 1, 2 cases, right? One becoming 1 previous state, 1 remains as 1. 1 here is set case. Now, what must be the inputs at that time to get these cases? You can write down. So, I want 0 and the Qn is already declared. Qn bar is how much? 1. Yeah, I'm sorry. Here, to get previous state, what must be J0, K0? So, Jk, so 0, 0. To get reset condition, J0, K1. To get toggle, J1, K1. To get set condition, J1 K0. To get toggle, J1 K1. To get reset condition, J0 K1. Previous state, J0 K0. Set condition, J1 K0. Repeat. Previous state 0 0, reset 0 1. Toggle 1 1, set 1 0. Toggle 1 1, reset 0 1. Previous state 0 0, set 1 0. Based on that, just give the inputs over here. J constantly 0. K 0 1. K bar 1 0. Q1 is 0 in the sense Q bar is 1 anyhow. So here, J constantly 1. K 1 0. So 0 1. K bar right. So Q1 is 0. Q1 bar is 1. Here, J is 1 or 0. K constantly 1. So K bar would be 0. Right? So Qn bar. Q1 is 1. Qn bar is 0. The last case, K constantly 0. So K bar must be 1. So J could be 0 or 1. Qn bar. Q1 is 1. Qn bar is 0. Over. And these are how the outputs obtained. So 0 into something is 0, 1 into something is 0, 0 plus 0 is 0. Here also story is same, 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus here 0, 0, 0. 0, 0, 0. 0 plus 1 is 1. 1 plus 1 is 1. Over equated the best ones. Now why don't you make it shorter table? 0 or 1. 1 or 0. 0 or 1. Like this. So shorter table here is Qn plus 1 for which defining Jk. That's what excitation table, right? Excitation table in a shorter way. 0 0, 0 1, 1 0, 1 and 1. For 0 0, J0, K could be 0 or 1, don't care. So J1, K don't care. J don't care, K1. And don't care, 0. Right? J0, K don't care. J1, K don't care. Don't care 1 and don't care 0. Most important one to remember, to use it in maximum number of cases in the counter designs and many other cases. So JK excitation is 0 0 0x, 0 1 1x, 1 0 x0, x1, 1 and 1 x0. I repeat, 0 0 0x, 0 1 1x, 1 0 x1, 1 and 1 x0. And SR excitation, hope you remember, 0 0 0x, 0 1 1 0, 1 0 0 1, 1 and 1 x0. And all this you must be remembering well to do the best in your upcoming circuits. And after this, we still have the design of T flip-flop and realization of one to others. And you have synchronous and asynchronous inputs. And you even have racing and elimination, master-slave flip-flop. The second part is application-oriented. Let us just do the best over there also. Once let us rehash the topics we learned today. Yeah, here please. Latch and flip-flop definition. So both are storage elements. Storing 0, reset, the storing 1, set remaining in previous state. With control is latch, without control is latch and with control is flip-flop. That's what we declared. And next, we just had an analyzation that why the basic SR latch having 4 NAND gates. 2 for inversion, 2 for storage. Why the inversion is taken? For that, we have a detail. What's wrong in inversion? Inversion, adding 2 gates for one small bit storage is increasing cost, complexity, delay, lot of parameters as we said. And we just come back to design with only 2 NANDs unchecked out. So basic RS with only 2 NANDs unchecked out. So 2 NANDs diagram has got a drawback of, you can just see here. What is that? 2 nines got diagram got a drawback of unnecessary forbidden state yet low power consumption. Very much unnecessary previous state yet high power consumption. To just reverse them, unnecessary at high power, previous at low power, because previous state is most useful requirement, frequently used requirement, constant requirement. To get previous state into low power, so we have inverted the inputs and checked out. After inverting, a new picture, new drawback has come into the picture, that is R1 getting set, S1 getting reset. R1 it should be reset, but R1 it is getting set, S1 getting reset. To overcome that, we have again interchanged the inputs, invert and interchange. Finally, basic RS with 2 nands has become basic SR with 4 nands. I repeat, basic RS with 2 nands become SR with 4 nands. Again, we went with that. The SR with 4 nands, truth table, character equation, excitation table. For every flip-flop, these three are common. Truth table, excitation table, character equation. Truth table is input to output table. Character equation is a math relation between input and output. Excitation table is output to input table. All these three we have seen for SR. And here is SR excitation. And then we went with the SR flip-flop. Latch is becoming flip-flop by adding a clock, where clock is acting like control switch. And then we made a delay flip-flop. SR flip-flop updated as a single input switch by taking the feature of Qn plus 1 equal to S when S is not equal to R from the table. So we created S is not equal to R condition to make a delay flip-flop. So this is only the one being called as a delay flip-flop, because here delay is only the main action, none others. And similarly, we have seen SR updated as JK. So JK flip-flop is nothing but SR modifying forbidden condition as a toggle condition. Remaining 6 are same. Modifying forbidden condition as a toggle condition. So we have seen that, how we could do this. JK requirement, SR excitation, and finding SR from the map, and then drawing the circuit. In equation Qn bar, but connections are Qn plus 1 bar and Qn plus 1. The reason is the connections would be the same, but the bit appeared will be the previous bit always. And NAND becoming, and the inverter is becoming NAND. Similarly, and inverter is becoming NAND. This is how the circuit is. And then JK truth table, JK character equation, JK excitation table. And all these are well done. So JK character equation is JQn bar plus K bar Qn. Later after we have T and others to continue. Thank you.